out to a well-ordered planetary system has been established for decades. However, there are still many puzzling details that are keeping refined by our new observations. In particular, the successful search of exoplanets has revealed a surprisingly rich diversity in those planetary system architectures. And this diversity is very likely rooted in these conditions that foster those planets. Well, meanwhile, once young planets are formed there, the interaction with the disk material will imprint signatures that we can observe to infer the presence and properties of those systems, which is particularly helpful to confining the planet formation models. So when we look at the assembly of a planet, the dust particles are very essential. So starting from the ISM dust, grains has to grow about 14 orders of magnitude in order to form an Earth-sized planet. So as you can imagine, this is a huge challenge. So the first challenge comes to the so-called radial drift problem. This is because the gas particles in the disk, they can feel the pressure force, while solids, they won't. So the aerodynamic drag induced by this velocity difference will push those particles moving towards the region of high pressure that is close to the star in a typical smooth disk. So the problem of this process is that it happens so quickly that we run out of materials to build planets. There has been many hypotheses, and the very interesting one is that we can think of the disk as consists of multiple local pressure maximums instead of having just one central peak close to the star. So in this way, larger grains can accumulate locally in those pressure peaks and sustain at large radii. This is very neat hypothesis. But for a while, for a long time, it's only a hypothesis. So, well, recently with ARMA, we are finally close to this answer. So here I'm showing more pretty ARMA images of disks. As you can see that we find so many beautiful rings and gaps, and those astonishing images telling us that disks are not smooth at all. They are actually highly structured. And those bright emission rings with high dust density were believed to be important sites for planet formation. So in order to assess how planet forms, we can look at the grain properties. This is because simply the initial step of planet formation is just building larger and larger grains. So we can do this by looking at the spectral index of the dust emission within those particular high density regions. What we found is that in those regions, the opacity index or spectral index tends to reach to a local minimum in this high density peak. And that indicates the presence of larger grains. So great, those high density rings might have the optimal condition to form young planets in the future. Well, meanwhile, a lot of us are very excited about the idea that young planets will just hide in those dark, empty regions. So this is our current best knowledge of this young planet population of those hypothetical planets. They are not confirmed. So those planets are mostly low-mass Saturns and Neptunes at wide orbits. This idea is very interesting because we found some real evidence. We do find young planets in at least one of those targets in the inner cavity of one system. But the sad news is that we haven't found many of them. Well, given the current detection limits, as Sebastian just talked this morning, we're only at the order of a few Jupiter mass. So this non-detection result is not that surprising. So currently the roles of substructure, either as signs of planet formation in the future or as indicators of existing planets, is still under debate, or they happen at the same time. Well, people tend to believe that, okay, substructure has to be universal in disks. But I say, okay, we should wait for a while because this conclusion is mainly based on a limited sample of disks that do have high resolution observation. So this sample is now, I plot them as color dots in this diagram. So as you can see, immediately there are a few problems. The first one, for some targets, even though they have been observed at high resolution, they still appear featureless. They are kind of smooth in image. Those are those blue dots. So those targets are surrounding the same type of stars and have similar disk brightness compared to other ring systems. What happened to those targets? And the second or even present issue is that our current observations are heavily biased to those bright disks around more massive hosts. And M dwarfs, which is a very important planet hosts, have barely been touched. So how planet formation condition might be different from their solar counterparts is largely unknown. And so my research is mainly focusing on to understand those questions. So for the first part, we found that when we're looking at those systems, so many of those smooth disks, we call them smooth, that they're much more compact than the larger one, than the ring disks. So here I'm showing only two examples. One is a large ring disks, another one appear featureless and small. If we can ask ARMA to give us time to look at them in more detail, we can find that, okay, they indeed show some features in the inner part. In this case, with 3 times better resolution, for us, it's a deep gap at 5 AU. So at least in some systems, it's simply a matter of resolution. Well, for those two types of systems, even though they may have the same condition to form planets, it's still a question why some are so big and why some are so small, because that may affect what type of planetary system they can build. And that is also one part of my research. Now we are also starting to explore the disks around M dwarfs, trying to prove this empty parameter space. So here I'm showing some initial results. I should mention that disks around M dwarfs, they are generally much fainter, as you can see, and they are so much smaller in size. Proving them requires even higher resolution. So that's why it's barely explored in the initial stage. So here, this results showing our sample of 6 targets. We found that in 4 of them, they all show substructures. And it's very interesting that 4 of them have inner cavity, have deficit of emission in the inner region. So I'm not sure if this is just a coincidence or there are some important differences of disk evolution around different types of stars. And that's a very interesting question to explore. Well, I think all those results emerged telling us that substructures might be a very important piece to guide planet formation. Finally, I want to shift the focus to a particular famous target, the Casson 15. This is the first system that protoplanet candidates have been proposed back to 10 years ago. And since then, there's a lot of debate. And recently, we may have found new evidence of young planets in this target. So here I'm showing ARMA image of this target at 2 different wavelengths. So basically, they're the same. They have 2 very bright ring structure. And if you look closely, there's another faint one in the cavity. Now, if we can zoom into the inner part, we can find that the inner ring is actually not homogeneous. It has like 2 prominent axis emission features that are separated by roughly 120 degrees in azimuthal direction. We can also have a more closer look at the 2 features in the residual map. You can see that in the residual map, the 2 features are both significantly detected at 2 different bands. And this makes our detection quite robust. So we are very excited about this finding. This is because similar patterns have been long predicted in planet interaction simulations. So it could be used as a smoking gun of planets there, but lack observational evidence. So the idea is that when you have a planet, it interacts with a disk, it pushes material away from its orbit. But it also leaves a small amount of material co-moving with it. So it forms this so-called horseshoe orbit. And when conditions allows, material will be preferentially accumulated in the Lagrangian point in this star-planet system. So we are finding very similar patterns in our data compared to observations, compared to simulations. And also there are many other evidence that supports our results. I don't have time to cover here. So we propose a scenario that the fainter ring observed is actually a horseshoe ring. And we're actually catching a young planet in the making, which it sits just in the middle of the two features. So I think this technique has the advantage that we know exactly where the planet is. So that will help us to guide the future search and the characterization of such planets, such planet candidates, I would say. And so to quickly summarize, I hope I have convinced you that substructures is indeed an important piece to help us understand how, when, and where planets should form. And it has a bright future. We should take a more closer look in such features to understand how planets form there. Yeah, thank you for your attention. Happy to take questions.
Questions from the audience?
What is the other evidence that there's a planet in LKCA15?
What is evidence? There's no.
So you said there was other evidence that you didn't have time to talk about. What is the other evidence?
Yeah, sure. Thanks for the question. So actually, maybe you can look at this plot. This is the background is a scattered image that shows how the small dust grain distribute there. So right in this ring, there's no small dust grains. That means this low density area that has been expelled by the planet interaction there. Yeah. Also, we found that the outer ring, this first bright ring, it shows some signature that have two bands of observation, and at a longer wavelength, the ring is much narrower. That is evidence of dust trapping there that caused by that should be a pressure bump in order to have different distribution of different grain sizes.
Any other question from the audience? Questions online? No? Okay, so do we have a rough upper limit on the mass of the planet?
Yeah. So we think that this is roughly a Neptune or Saturn mass planet. Because the things that if you go in this, so here shows different models that have different constraints on the planet mass. If you have a higher mass planet, you tend to only show like launching point trapping instead of the full horseshoe ring. But it's very uncertain because we don't know how alpha looks like in the system. Yeah.
Okay. Well, if there are no more questions, then we can thank again. Next slide. No, sorry. Okay. So can everybody see it online? Sure. Okay, great. Okay, so we're going to our next talk from Fei Dai about 700 million year old precursor of the Kepler multi-planet system.
Thank you, Sebastian. So for those of you who do not know me, my name is Fei Dai. I'm currently a postdoc at Caltech. My research focuses on the most extreme planetary systems that look nothing like our solar system. And I believe in order to understand something as complex as planet formation, we need to look at the extreme cases to address our gaps of knowledge. Thank you. All right, and in this talk, I would like to highlight one such extreme system. A key prediction of modern planetary formation theory is that planets migrate as they grow in a disk. This is due to gravitational interaction between the planet and the disk. And in most part of the disk, the net effect is for the planet to migrate towards the central star. Now, consider you have several planets forming together in a disk. Then the heavier planets tend to migrate faster than the lighter ones, and there can be differential migration. And when there's differential migration, the planet can often be caught into a so-called mean motion resonance before they collide with each other. And mean motion resonance refers to the configuration where neighboring planets' orbital pure ratio are near some small integer, as shown here. In such configuration, the mutual gravitational perturbation the planet have on each other can actually phase up and accumulate over multiple orbits. As such, the resonant interaction actually acts as an effective potential well that traps planets together while they both migrate towards the central star. And this process can be repeated to form a chain of resonance as shown here in this schematic here. This process of resonant capture is so efficient and so robust that it is almost difficult to understand why the mature planetary system only shows a small fraction in resonance. For example, if you look at the Kepler sample, and the vertical dotted lines are the low-order mean-motion resonance, among the mature planetary system, only a few % of them are near low-order mean-motion resonance. And if you look at these near-resonance cases more carefully, shown on the right, they still deviate from perfect resonance by about 1 or 2%. So several mechanisms have been proposed to reconcile this tension between the prediction of disk migration, which consistently form resonant planets, versus the observation of mature planetary system, which consistently lack resonance. So one possibility is tidal interaction with the host star, which causes a slow drift of the planet orbital period ratio away from resonance. Or it can be giant impact collision, which is so violent it can totally disrupt the initial resonance to a non-resonant configuration. Or maybe it's something in between. The planetesimal scattering can both cause a drift of the orbital ratio as well as instability. All right, that sets the stage for this new discovery I want to talk about today. QI 1136 is a young sun-like star that hosts 6 transiting planets. And hopefully by the end of the talk, I will convince you that QI 1136 actually still records the initial conditions from disk migration. So according to the test light curve, we discovered 6 transiting planets with orbital periods between 4 days up to 40 days. Moreover, the planet are in a series of resonance with orbital periods ratio of 3:2, 2:1, 3:2, 7:5, then back to 3:2. So one thing we know pretty sure is that the system is young. This is according to the fast stellar rotation and the strong lithium absorption as well as elevated chromospheric activity on the host star. So our best age estimate is about 700 million years for this young system, whereas for the mature Kepler planets, their typical age is about a few giga years. Actually, the median age is 4.6 giga year. So I mentioned earlier, the near-resonant Kepler system still deviates from resonance by about 1 to 2%. If we look at QI 1136, the planet here deviates from resonance by just 10 to the minus 4 level, as shown by the red line or the red points here. This is 2 orders of magnitude closer to resonance compared to the mature Kepler systems. And with deep resonance, it was no surprise to us. We detected strong transit timing variations on all 6 planets. The deep resonance actually amplified the mutual gravitational interaction between the planets, and the periods are no longer perfectly periodic. And it turns out, by modeling these TTVs, or transit timing variations, there's a lot we can say about the orbital architecture. So coming back to the question of resonance, so far our discussion of resonance has focused on orbital period ratio. However, integer period ratio does not guarantee true resonance. True resonance is actually characterized by the libration or simply the oscillation of some resonant angle with small amplitude around some fixed point. As an opposing case is the case of circulation, in which the resonant angle explores the full 360-degree range. So what is this resonant angle? Well, the resonant angle is nothing more than generalized coordinate for the resonant part of the Hamiltonian, and it's given by a sum of the mean longitudes of neighboring planets. So instead of going to the mathematical detail, let's examine the geometric significance of libration of resonant angle. Let's take, for example, the case of the Galilean moons. Io, Europa, and Ganymede are in a mean motion resonance of 1 to 2 to 4. And their resonant angle is given by this equation here. And observations back a few decades ago already showed us this resonant angle librates around 180 degrees with a very small amplitude of less than 1 degree. And the repercussion is that whenever two satellites have a conjunction with each other, the third satellite is either 90 degrees or 180 degrees away from the other two. So the libration of the resonant angle here dictates there are no triple conjunction in the system, and this tends to promote long-term stability. And for TOI 1136, we are seeing pretty much the same situation here. The letter on the left shows the various resonant angle involving 2-body, 3-body, or 4-body. And the number in the brackets is a fraction of our TTV solution in which the resonant angle is in libration. And we can see for the low order resonances, they have almost order of unity probability of being in resonance or in libration. On the right, we're showing the time evolution of the 2-body resonant angle here. And you can see for nearly all of the resonant angle, they librate around 180 degrees. And the only exception is shown by the gray color, which is planet pair E and F. This E and F pair stands out because it is the only second order resonance here. And you can see the time evolution is kind of chaotic. It can change from a state of libration to circulation. So what is wrong with the second order resonance? Well, first of all, the order of the resonance is given by the difference between the small integer. So 7 to 5, difference is 2. Whereas the other resonance, 3 to 2 and 2 to 1, these are first order resonance. If you open any textbook on celestial mechanics, probably tell you that second order resonance is suppressed over first order resonance by another factor of orbital eccentricity. And for most planets we know, the orbital eccentricity is at about a few percent level. So that this represents at least 1 order of magnitude suppression in the strength. Moreover, if you look at the width of the resonance in semi-major axis space, the first order resonance, 3 to 2 and 2 to 1 here, are pretty wide in semi-major axis. However, the second order resonance, 3 to 2, are actually razor thin in semi-major axis, especially towards low eccentricity. So as such, the weak strength and the thin width of second order resonance means that they are really difficult to form during this migration. So our insight here is to convert that difficulty in forming a second order resonance into a strong statement about the kind of disk that gave rise to TOI 1136. We carried out a series of disk migration simulations. Won't have time to go into the details. But one key result we found is that we have to putting an inner edge of the disk to slow down or even reverse the direction of migration so that all the planets nicely captures into their observed resonances. Right. So an inner edge of the disk in reality is expected, at least due to the truncation of the disk by the magnetosphere of the host star. And the resultant pressure bump at the inner edge provides a natural way to slow down and even reverse the direction of migration. And very curiously, the innermost planet here, planet B, is on a 4-day orbit, or just 0.05 AU from the host star. If you ask the disk expert in the audience, they'll probably tell you this is exactly what one would expect the inner edge of the disk to be. So these 4 panels shows orbital Q ratio, the eccentricity, and the 2-body and 3-body resonant angles in our disk simulations. And what we found is that over a time scale of tens of kiloyears, we can capture all 6 planets into their observed resonances. And once they are in resonance, you can see the resonant angle change from a state of circulation into libration. Another point I want to make is that we found the disk that gave rise to TOI 1136 has to be less dense than our solar system's disk. Take, for example, the minimum mass solar nebula, which states that at about 1 AU, the disk that gave rise to our solar system has a surface density of about 2,000 grams per centimeter squared. But in our successful disk migration simulations, which gave rise to QI 1136, shown by the blue point here, all of them had a lower density compared to our sun. And we believe it is this low density that slows down the disk migration and enable us to capture a planet into a second-order resonance. So the final result I want to mention is that we also got an RM measurement, Rossiter-McLaughlin measurement, for the largest planet in this system, thanks to Gumi, who introduced the RM effect. I don't have to go into detail here. The bottom line is that the whole system seems to be coplanar, in which all 6 planets transit, and well aligned with the whole star. If the system were misaligned, they would be pretty much against the very delicate resonant architecture we found. All right, here's my summary slide, which I borrowed from Sean Raymond. So the current paradigm for small planet formation is that planet embryos grow and migrate toward the host star in a disk, and the end game is usually a chain of resonance anchored at the inner edge of the disk. However, if we look at the mature planetary systems, the vast majority of them has already gone stable and their resonance disrupted. So the discovery of QI 1136 at 700 million years nicely fills this gap in our understanding by providing us a planetary orbital architecture that is emergent from the disk migration before any subsequent evolution has disrupted the resonance. All right, I'll end here and take any questions. Thank you.
David, a really great talk. I had a question on some of the other young multi-transiting systems that have been found with us, or K2, like V1298 Tau, and some of the other TOI systems. Are they also, that we do see TTV systems, are they also seen to be in like super deep?
Yeah, at least so V1298, I think is only other young system where we have multiple transiting planets. There, they are near resonance. I think the deviation is 10 to the minus 3 level. So not as steep as 10 to the minus 4 that we have seen here, but deeper than typical Kepler system. And the trouble of understanding V1298 is the orbital periods are kind of long, so we didn't get as much transit to pin down the whole orbital architecture. I know additional follow-up work are being carried out to understand that system better.
Oh yeah, that'll be interesting. Thank you.
Are there any questions online? No? Okay. Anyone else that has a question? No. Okay, let's thank Fai again. Which of the 3 do you want?
Fine.
Okay.
The classic ones.
Okay, so we have a talk by Alexandra about the observational tests of early phase disk dynamics. So I will start.
Well, hi everyone. And so I put observational in here just to get some observers to pay attention, because I'm actually I'm a theorist, so my job is to tell stories. And luckily, I've been sort of set up wonderfully by several people to talk about disk dynamics in terms of less conservative terms. So we're going to go for some rampant speculation really fast, kind of on a broad coverage, because I think 12 minutes is a great way to handle that. So I'm going to wax philosophically a little bit. This is a painting by Vasily Kandinsky, who is a guy who got really into circles as this sort of fundamental way of human expression in terms of like you could think about an eigenvalue of human emotion. And he thought there was a cosmic significance to these circles. And I think that he shared a lot of characteristics with some early physicists who maybe whether through practicality purposes or through the fact that spherical things seemed really common at the time, had a tendency to kind of assume isotropy. But there are kind of limitations now that we find to this assumption of isotropy in how we form stars, planets, and so forth. So we have a really nice kind of basis for thinking about disk formation that's based in self-similar models of infall of material onto these systems. And they're in effect 1D. When you assume spherical symmetry, you're working in one dimension and you have averaged out all of these other effects. And so the idea is that with our favorite friend, the conservation of angular momentum, we know the radius at which material will be deposited if you know the initial specific angular momentum of these systems. We kind of know how the collapse will proceed over time. And we know that this actually results in a fairly smooth disk with these characteristic radius signatures, which, as we've heard today, smooth disks are actually quite uncommon. And so I'm here to sell you on the, of course they're uncommon train, because there's actually a very natural way to not produce smooth disks, and that's because star formation is an inherently 3D process. So we've seen that kind of yesterday in a lot of talks. Everyone has a lot of very messy clouds. And so actually, from the star formation theory perspective, which is my PhD home, theoretically speaking, is I did these models of star cluster formation. And what we really found in these simulations, I and a lot of other people, honestly, once you start to really look for this, is that the accretion onto protostars forming in these simulations, if you actually tracked it, it is very episodic, it is very anisotropic in that most of the time, you are accreting in sheets and streams. And so I've talked about this before, because this is kind of my hobby horse, is that there is a filamentary episodic nature to this type of accretion. And so if you actually kind of go back and look at the statistics of all the stars you form in the simulation, and you kind of look at, well, it's episodic, so how long does an infall episode last? And what's the velocity that it's falling in at? You can derive a length scale from which you are accreting. I'm not the first one to do this. This is now kind of a common practice. And so we can predict the scale at which you will most likely see a lot of material cohesively streaming. It's about 10,000 AU. And here's some vindication from the past and something more recent in which this new phenomena in which we've dubbed this sort of anisotropic behavior a streamer. And you can actually see that this behavior continues down onto 100 AU scales onto the disk as well when you look at denser tracers closer to the disk midplane. And so this is my real hobby horse, is really connecting everything in this multi-scale anisotropy. So just like we see in larger scale star formation simulations that your outer boundary conditions really matter, and they sort of cascade down to lower scales, we also see this when we actually look at protostars. So there's been some work observationally from Elviro Hakar. He's found these kind of velocity coherent little bundles called fibers. I would call them flows, but that's just me. They're about 30,000 AU in scale, so I'm winking very emphatically at that scale. And that's actually, if you look at a protostellar core, like this one in Ophiuchus, it's about 30,000 AU in the dense dust. And in that same core, this work by Dominique Segura-Cox shows that there is actually a suggestion of substructure for a source that is very, very young. This is an embedded source, 100 million years old at most, right? And here is work by Jaime Pineda, which shows another, again, 10,500 AU streamer in HCN. So this is in the molecules. And so my kind of thing that I want to say is, like, really, this should be ubiquitous. And just as we're now learning that substructure is ubiquitous, it pays to really think about the story we've been telling about planet formation and star formation for many years. And so I'm here to show you that, well, disks are really dynamic objects. We like to say that they're steady state because it's a lot easier for us. We like to have a nice viscous model with one alpha. Disk theorists love an alpha, but I'm here to show you that this is probably not likely. So here I'm dropping some material onto a disk from my paper earlier this year, and we're creating a lot of dynamics. So this is the surface density in the gas, and these are actually velocity deviations that one can expect during this process. And you form essentially these spiral rings in this zone. You form one vortex kind of on the inner edge, one on the outer edge. And you create a whole lot of mess. And so if you kind of neaten it up in 1D over radius, what can we actually expect in terms of planet formation and in terms of disk dynamics? So the first thing here is that we form pressure bumps robustly at the inner and outer edges of infall. And these pressure bumps, as we've heard before, are really quite vital to trapping the dust that you would need to create planets in those locations. You also drive a crap ton of turbulence all by yourself. You don't need a little viscous disk alpha, the properties of which depend on the properties of the infall and the local disk properties at which you are dropping this material. So now this is getting more complicated, and here's where people are like, oh no, this is so model dependent. There's so much stochasticity. And yes, I also worry about this too. I'd like to solve this problem. So if you'd like to talk to me about this later, I would love to. So right, you've got your dust drift barriers, you've got your vortices, your spirals, they drive your disk transport. When you increase your turbulent alpha, you might also induce more collisions, i.e. make planet formation more likely and faster. And so we kind of stop it. We can see we have beautiful structures and beautiful ways to trap dust due to this drift dynamic equation. And so here is something I've been working on recently in which I became fascinated with the question of, well, a lot of this dynamics depends on these inherent disk properties that we actually have a really hard time measuring, like disk mass. And if you don't have a ton of envelope, such as in a late stage infall system, it's actually quite difficult to see, but you can have 1% of your disk mass actually do quite a bit to your disk. So something that people like to model away is like, oh, well, there's really not that much stuff there. So what'll it hurt if we don't put it in? Well, dynamically speaking, so these are actually surface densities across this parameter space, along with the 1.3 millimeter continuum image, just to show you that you'd see it. And you can actually see there's a diversity of structure. So the first structure is a classic non-axisymmetric structure, a vortex due to an RWI, so you get a lot of non-axisymmetry in some of the rings. But you also see in this region, you are actually much more axisymmetric. And that's in a situation where the way I've designed the study is to target it so that you're only adding 10% of the disk mass according to the infall rate, which means that if you don't have a ton of disk, but you have a high infall rate, you will be done very quickly adding that disk mass. So within that constraint, can we actually induce the RWI that would form the vortices? The answer is in some of these systems here, you can't. And in fact, you just end up plopping a bunch of stuff down there and you create a diffusion-dominated dynamical ring. There's also evidence that when you have these vortices, if you include the dust-gas back reaction, you might actually break them up and they would become more axisymmetric over time. And the time scales, if anyone wants to talk about this, I will be happy to, but there's a lot to say there, so I'll move on. And so in general, I think we've seen a lot of really nice photos and images from the radio, and here's some more of these dust continuum showing structures in the disk. So a lot of non-axisymmetry, a lot of very large scale outer disk structures, right? And so maybe I'll say vindication once more, although again, this is me kind of waving my hands wildly because there's a lot of disks and very unique conditions, caveats ensue. However, if we're drawing a broad brush picture, there is certainly something to suggest that these are signposts that we could be looking for in terms of putting this story together. And this actually includes both. These are class 0-1 systems, which are thought to be younger, and these are actually more later stage systems, and they both show evidence of this kind of non-axisymmetry. So, for the past year, I've really been kind of trying to sell, star formation's messy. We know that streamers should affect dynamics at early times, like I wrote a whole paper about it. It should happen, and that you should have structure formation early and often, really, because again, I'll remind you, infall is episodic over the lifetime of star formation. And so this is my cartoon to think about, and this is the paper. But there's this other thought, been swirling in my head. So dust continuum is really favoring the disk structure, but this molecular line emission might tell us a different story. So this is actually an object from a paper by Sarah Grant, which shows that most of your millimeter continuum is in this little tiny disk region, but at, again, around 10,000 AU scales, you have molecular things that could be inflows. I'm not going to make those claims for anyone else. I'll just, again, wink with emphasis. So I began to think about, is there a way to combine our understanding of what's going on dynamically in the dust continuum with the fact that we now have really much more information about things like temperature structure, for example, from the molecular line emission. And so the MAP survey actually nicely got the same transition in 3 isotopologues, which means that they all appear at different optical depths. They've isolated some what they call disk surfaces with a Rich Teague's disk surf code. And what they've extracted is a 3D-ish, somewhat vertical, distribution of brightness temperatures. And so if you remember your radio interferometry from grad school, your brightness temperature is just a Rayleigh-Jeans, extrapolation of your intensity, but it could be with some radiative transfer magic somewhat related to your gas temperature, right? And so what I really have been kind of doing a lot of, whether this is a foolhardy venture or not, is thinking about how we can take a dynamical model that I've run for many, many different cases, has an envelope solution of the envelope that is causing the features exactly, and then it's fully self-consistent that way. I can shove it into some nicely post-processed radiative transfer code. This is RADMC, for anyone wondering. And out of it, you can get out both radiation fields as well as the dust temperature. You can combine that information, try to put a little PDR model, get a gas temperature. So now you have several components in your dust populations as well as distributions of your gas in fully 3D. And this kind of provides a framework to really test about which observables are going to be sensitive to these dynamical properties. And so far, I found that there are situations in which you can actually isolate a region of disk mass and envelope mass space just by kind of doing the work of being consistent all the way through and actually collecting the observables along the way. Because there are systematic effects, and now with all of these really nice spatially mapped disks in molecules, it's a whole new world, so to say. And why should we care? And this is for the planet folks, is really that this is a stochastic system with a lot of substructure. And if you're someone who, again, has been, the lies we tell each other, I think, are the ones where we say things like, oh, the C/O ratio in a planet's atmosphere corresponds to its formation location, which isn't necessarily false, but it's not a smooth distribution of thermochemical conditions throughout this disk. It's a highly changeable set of thermochemical conditions that are changing on dynamical timescales. We can no longer say a planet can form in steady state in one location. I don't know if that's too spicy of a take, but that's what I believe. And I think actually there's a lot of evidence for this from our own solar system, right? There are meteoritic, sorry, I'm going over, constraints, I'm almost done, that actually tell that there's a specific timeline, and we have to have compositional heterogeneity. So when you actually time meteorites, which you can do very, very well, meteoricists have much better error constraints than we do astronomers. They actually told the story that you need additional infall of isotopically distinct material from your cloud to explain that you have these two different chondrite populations in your meteorites. They have the timing. They know that you have the planet formation ongoing as you segregate these reservoirs. And they know you need to have multiple events to form these things called chondrules, which require that you heat a disk for a very short time, but over and over and over again. And I'll just remind people that when you drop stuff on a disk, you can do a lot to it thermodynamically, that spirals also tend to heat and shock, and these are interesting dynamical effects that we can look for in signposts such as our own solar system and in other systems. And also, usually kind of Jupiter is sort of invoked for this segregation, but this is my personal opinion, is that you can actually just do both, right? If you drop a bunch of material, you create a pressure bump, you segregate the reservoirs anyway. You don't need to really, you can make a Jupiter, but you don't need it there. You've already 2-in-1. You get a 2-in-1 with this, as well as the fact that you've got your multiple epochs. So to close out, here's my Kandinsky vindication in that he also eventually stopped with the circle and realized the beauty of a streaming form. And that I've talked about kind of 4 potential signposts that we can be looking for in how we talk about planet formation, namely these large-scale inflows, the disk dust substructure, spatially mapped molecular line emission, and how we think about the composition of solid bodies. So, thank you.
Okay, we have time for one quick question, if there's one in the audience. Is there one online? No. I do have a quick question, is that the velocity deviation maps that you showed, can they also explain like the kinks that we see in the ALMA velocity channel maps? Because they're currently being used to as an indirect measurement of planets.
Well, thank you for that question, because yes, this is also part of my hobby horse. I think that when you have a very clean, only one signal velocity deviation, that bears more towards planets, but when you have multiple rings and you have to look for that deviation with respect to a ring position, it becomes a lot more trickier. And in my paper, I actually talk about kind of, if you're looking in the wrong ring, because of the velocity flips and the multiple vortices and the interactions, you could potentially confuse the direction of the signal. And so it produces similar magnitudes, is what I'll say, in deviation.
Let's thank Alexandra again. Okay, and after this, we're switching to the last scientific talk of the symposium. From just press the button. Yeah, from John Zink. Oh wait, I need to. Yeah, I think you can share your screen.
Okay, I think it's shared. Is that good? I don't know. Probably need to do that. I look good?
Yeah, it looks good. And we can also hear you. So,
all right.
Talk to us about the galactic influences on planet formation. So, go ahead.
Sounds great. Thanks, everyone. I'm John Zink. I'm a Hubble Fellow at Caltech, starting my 2nd year now. I'm going to be talking about exoplanet demographics, and I'm really excited to really close out the talks portion of this conference. So thanks for sticking around. Okay, so I want to start by reminding everyone that large-scale surveys really provide us snapshots of different parts of planet formation. And really, we want to answer 2 underlying questions about planet formation. How do planets form, and how do their orbits evolve over time? Now, the goal of demographics is to hopefully take all these snapshots, put them together, and create a coherent story of planet formation and evolution. The bread and butter for doing so is usually the Kepler mission, because it stared at one patch of the sky for 4 years, collecting photometric data, and really providing us a nice homogeneous sample of planets to kind of carry out all these demographic studies with. And so looking at the Kepler sample, we really could divide planets into 4 different classes. We had super-Earths, sub-Neptunes, Jupiters, and sub-Saturns. And for each of these different classes, we found somewhat unique occurrence distributions. So here I'm just kind of showing what was found with the Kepler mission. I don't have enough time to go into detail on what these different trends indicate, but you can see this is planet occurrence as a function of period. And you can see there's some diversity amongst these 4 different populations, which are quite interesting and very informative about, disk structure, how planets evolve and kind of change over time. So upon a malfunction on the Kepler spacecraft, the K2 mission was born. And this mission was really quite wonderful because instead of staring at one patch of the sky, it looked at 18 different fields across the ecliptic. And this gave us a much wider range of galactic latitudes, stellar ages, stellar masses, and stellar metallicities. So we could really see how these different stellar parameters played into planet formation and therefore planet occurrence. So coming back to our distributions from the Kepler mission, let's lay on top of it our K2 values that we found. So laying the K2 values on top, it looks pretty similar. There's not a wild difference here. And this was not totally surprising. You know, we expected maybe the Kepler field was rather representative, but we were a little surprised with how well most of these different distributions matched up. The big takeaway from this study was that we were able to say, okay, it appears that anywhere we look in the local galaxy, we're finding roughly the same number of planets. So it seems like most of our findings from the Kepler sample can be taken to the bank and kind of applied broadly across the local galaxy, which is great because we learned a lot from Kepler. And that's wonderful. So let's dive in a little deeper and see if we can kind of parse out a few more interesting trends found with demographics. So let's think about the stellar parameters and how they could potentially impact planet occurrence. So looking back, early ROV surveys kind of noticed this interesting trend that as you move from lower mass to higher mass stars, there appears to be this decrease in planet occurrence. And this is seen for pretty much all of these 4 different classes of planets. This is kind of surprising because the naive idea might be that as you move from lower mass to more massive stars, you're going to have a more massive disk. And therefore, you might think, well, shouldn't there just be more planets created because you have more material? But that seems to be not the case here. And that's quite interesting and not completely solved why that might be. So that's an open question that we're still looking into, but it was identified with demographics. We're verifying it here with Kepler and K2, finding that similar trend is strong across all 4 of these different classes, with somewhat of a negligible trend for the Jovian planets, where maybe disk mass is relevant here. Another interesting stellar feature that is impacting planet formation and planet occurrence is the composition, or Fe over H, the metallicity of the star. When we look at the metallicity of all of these different stars amongst the Kepler and K2 population, we find these interesting trends for our 4 different classes of planets again. It seems that as you increase the metallicity of the star, you increase the planet occurrence. So again, this is a proxy for potentially the disk composition and what the material is made up in the disk that could potentially form these planets. Again, some of this was found with early RV surveys, definitely for the hot Jupiters. There was a strong trend. Some of the sub-Saturns, these were strong trends noticed early on. But we were able to kind of verify this again with Kepler and K2, that these upward trends tend to agree for both the sub-Neptunes and the super-Earths as well, albeit they are much weaker, but they are still there. So these were kind of the 2 features that we think about. We have composition and the amount of material you have. And these seem to have kind of interesting implications for how planets may or may not form. So these were 2 known features discovered with the Kepler mission previous to my work. And what I want to talk about today is a new parameter, a 3rd feature that we're just starting to be able to think about. And that's galactic location. So this may not be obvious. Why would galactic location matter? And I want to kind of walk through why I think galactic location is an important feature in planet occurrence and therefore planet formation and evolution. And this is really work that's only available now that we have the Gaia sample. Particularly Gaia DR3 really allows us to do this work. And so to motivate this, I want to look at the distribution of planet hosts as a function of age. So we can see that it spreads a quite large amount of time, tracing its origins all the way back to essentially the beginning of the Milky Way. So we have known planets that were born right after the birth of the Milky Way. This is being the Genesis planet that I'm showing here. So this indicates that since the start of the Milky Way, we had planet formation occurring in the galaxy. And so throughout this process of galactic formation, a lot is going on. So at about 12 gigayears ago, the thick disk starts to form. And in this era, we have heightened alpha element abundances. Type 2 supernovas are dominating, impacting the stellar population and likely impacting the planet population as well. Moving forward, the halo starts to form in the galaxy 11 gigayears ago, potentially capturing stars that may have been, ejected from other galaxies that were disrupted and things like that. And then finally, the thin disk is formed about 8 gigayears ago. And in this era, type 1a supernovas start to kick on. And now we have a high Fe over H abundance that's really dominating. So this might be the era of more of these, Jovian planets, so to speak, because we have a stronger dependence on Fe over H for these planets. So you can see by this histogram here that planet formation is happening as all of this is going on in the background of the galaxy. So could it be that some of these features are kind of overlaid into our planet sample or our demographics of the planets as well? So looking at our K2 and Kepler sample, we can see these white dots are essentially the FGK dwarfs, and they span both the thin and the thick disk. So we can start to probe some of the oldest stars in the galaxy. So a lot of the work done by the previous talks think about the youngest stars and what we can learn from the youngest stars, because we can see direct evidence for how planets form. I'm going to argue that we also want to think about the absolute oldest stars, because they tell us something about how the galaxy itself is impacting planet formation. And so now I'm just going to run through some quick results that we had looking at galactic scale height as a function of planet occurrence. So that's just being the z direction away from the midplane. And where Gaia really comes in here is it allows us to kind of correct the scale height from current location to what the maximum location is going to be, because these stars will oscillate up and down above the galactic midplane, and we kind of want to correct for that, right? We don't want to be contaminated by a bunch of stars in the midplane that are going to oscillate much, much later to a really, really high scale height. So Gaia really enables us to correct for that. So looking at the Jupiter population, we see a minor downward trend as we go up in absolute galactic scale height. Now, this is kind of a weak trend, and the first thought that might come to your mind is, okay, well, we go up in scale height, we're also going to go down in Fe over H, so maybe we're just seeing a reduction in occurrence because of metallicity. And this plot here is indicating exactly that. We see that the strongest component of this downward trend is this Fe over H parameter. It's really dominating it and causing us to see this deficit of Jovian planets as we go up in scale height. So let's move to the next class of planets. The sub-Saturns. This trend's a little messier, but it is somewhat downward, as we can see. It doesn't seem like metallicity is necessarily dominating this trend, but it looks like spectral class is a bigger one here. And the reason that's important is because I showed there was this downward slope in spectral class. So basically the hotter stars have reduced planet occurrence, and hotter stars tend to be easier to observe when we think about things that are high up in scale height. And so this trend here seems to be, again, mostly dominated by this spectral class occurrence feature. So far, nothing new. It seems like everything we knew about spectral class and metallicity have kind of dictated exactly what we'd expect when we think about going upward or downward in scale height. So the sub-Neptunes, here's where things start to get really interesting. We see a really strong downward trend for the sub-Neptunes with planet occurrence as you go up or down in scale height. It doesn't seem like that's something that's dictated by the Fe over H, considering that trend's quite weak for this population. Spectral class plays a little bit into it, but it's not the dominant parameter here. We need to introduce this third scale height parameter that kind of accounts for this Z max value. So it seems like as we go up in scale height among the galaxy, we're finding fewer and fewer of these sub-Neptunes in the planet or in the stellar population. Moving to the super Earths, we're finding a similar downward trend. Again, it seems like we need a third scale height parameter to really fully describe this downward trend. So this is really an exciting finding. It's kind of interesting because we're looking at K2 and Kepler, these missions that have been dormant for many years, and we're still finding these first-order discoveries within this data set. And so the big takeaway is that thick disk stars tend to host fewer sub-Neptunes and super-Earths. And it's not completely clear why this might be, but presumably it could be a change in disk composition, alpha element abundances. Potentially there's some stellar evolution or a proxy for stellar age that's kind of reducing these smaller planets, potentially early on perturbations from when they're in globular clusters, much more densely packed star formation regions. And potentially galactic dynamics are playing here, right? The stars are not fixed in radius. They may migrate inward or outward. And this migration might impact either the composition or the system evolution over time and impacting our planet occurrence rates. But the big takeaway here is that planet occurrence is address dependent. It doesn't look like the same occurrence is happening everywhere as we are looking in this one part of our galaxy. If we go up too much or down too much, things change a bit. And that's really a relic of how the galaxy is impacting planet formation. And so the big takeaway here, and just to summarize my two big results here, is that the Kepler field and the K2 field are rather similar. So we can kind of use both of these populations together to really get more refined results out. And it also tells us that the K2 or the Kepler field was really representative, which is great. And then the second big thing is that planet occurrence seems to decrease as we move away from the galactic midplane, indicating that the galaxy itself is somehow impacting planet formation and or occurrence over time. So with that, I will conclude and take any questions.
Are there questions in the audience?
Hi, John. This might be a dumb question, but I don't know anything about planets, but I think a lot about metallicity. Why is there a trend or not a trend with metallicity and planet type?
Sorry, I'm not sure I totally got that.
Yeah, so as you stepped through the planet type, whether it was a Jupiter or Saturn or more of like an Earth type planet, yeah, there was sometimes a trend with metallicity and sometimes not. Is this just a cooling efficiency argument?
This is more of just a selection effect, to be honest with you. This has nothing to do with like the actual populations or not. When we have these Jupiters and the sub-Saturns, we don't have a ton of these planets. So sometimes we have some that are, have these strong metallicity dependence, and sometimes we just have most of them happen to be very metal rich. And so the dependence doesn't really play a big role in our galactic scale height calculation.
All right, thank you.
Does that make sense?
Yeah.
So this is kind of just connecting a few of the talks that we've heard over the week. Were you here for Catherine's talk a few days ago about bubbles and star formation in the local universe?
I may have missed it. I'm sorry.
I was just wondering if you would relate what you're finding with what she was finding, and I'm guessing that's maybe a filled question. So anyway, I was just going to, if you heard that talk, basically she found that in the local bubble, all the stars were forming on the bubble. So I was just wondering if that related to what you're finding here at all.
Yeah, it's very possible. I mean, definitely, I think there's a lot of talks that have happened this week, which are really we're all kind of coming to the same conclusion that we can't just assume planet formation and planet occurrence is uniform throughout the galaxy, right? This is all happening with the galaxy formation occurring in the background, and it can definitely impact how stars form and therefore how planets form as well. So it's not all in isolation.
Hey, John, really cool study. It's Mike Wong. I was wondering, I see this fine print here within a period range of 0.5 to 40 days. I understand you probably don't have data for longer period planets, but can you use this kind of study to make a prediction about longer period planet occurrence rates?
Yeah, so the reason we're using 0.5 to 40 is just so that we can use a comparative sample with K2 and Kepler. Kepler obviously goes a little bit further out, but K2 does not, so that's the hard cut on K2. Yeah, I think there's a lot of good work that can be done here. So one of the predictions are, one of the things I think is a really interesting avenue to think about is this idea of stellar evolution. And so potentially what could happen is that you have a lot of stars forming in more tight globular clusters early on, right, in these like thick disk regions. And that alone doesn't necessarily remove planets by any means. But if you have a distant giant within the system, they can be easily perturbed by these very nearby stars, causing all kinds of instability to the inner system and potentially removing and ejecting a lot of these inner planets. So that's one hypothesis that I'd like to look more into that I think has some potential to it.
Thank John again. We're through with all the scientific talks for this week, and I think there might be another announcement.
Yeah. Sharing?
Yeah, I think it has stopped sharing.
Okay, yeah. So I'll probably take my glasses off with it. Mm-hmm. There we go. The green dot, okay. Is that okay? Then yeah, it's PDF. So, Flory, Sharita, and I don't know if Darlene's with us. Thank you so much. Thank you for helping. You did a tremendous amount of work for us, and we really appreciate it. Thank you. And thank you to our friends on the AV team, Thomas Marufu and Kevin Finn. Back there, and we'll be sending lots of other people from the grants and the people who gave you tours. We'll be sending them all thank yous. But we want to thank the SOC, Elias, Erica, Leah, Anwar, Gudmundur, Mike, thank you. And special thank to Elias and his drone. And thank you to all the fellows. You know, we wouldn't have a program if it weren't for your science, but you have also done a lot more besides the science. You've done a lot to make the program better, right? You've really helped through things like the anti-racism, the mentorship program, resources for applicants. We really appreciate this, and the community really appreciates it and notices it. And so thank you. And you know, some of you will be alumni quite soon. Please stay involved if you'd like to. We would love to have you as continuing members of the community and helping the program grow and prosper. And so thank you from all the leads. So from Dawn and Paul and Katie.
I just also wanted to say, if you are not soon going to be an alumni and you are at all interested in helping to continue the movement that a lot of the third years have started, and they've really made the program a lot more visible in the community, and I've just heard glowing reviews and glowing comments from headquarters, from folks in the community, people that didn't even know the program existed. They're leaving. Hopefully they'll stay involved, as Andy suggested, as alumni, but we really need the current fellows to take up the mantle and try. And I know you all are super busy, and this is voluntary. We can't give you anything, but except the satisfaction of knowing that you're helping the community. And it looks good on your CVs too, I'd imagine. So anyway, please, for those of you who are not finished with us, please consider helping out.
Until then, enjoy the coffee and goodies.
Yes, and we'll be back for open mic,
Good mic.
basically at the top of the hour. So
Right.
please come out. Yeah, 4 p.m. Yes.
Oh, great. So that means you're not all of it.
No, Paul has cajoled many into. Yes. So thank you, everybody. How do I get rid of that? Okay, can you get rid of? Because I don't. It just. Yeah. I don't know how I did it or what it is. That was our biggest problem. So yeah, thank you. You guys all yes.